welcome to this episode of Aerospace Tech Talks, where we explore the technology shaping the future of space and national security. I'm Kevin Bell, Senior Vice President of the Engineering and Technology Group here at the Aerospace Corporation. And today, we're talking about a topic that's getting a great deal of attention across the space community: radiation effects and how we test for them. Whether you're launching communication satellites into low Earth orbit or building long-duration systems headed for deep space, there's one truth that doesn't change: space is a harsh environment. And the radiation effects on microelectronics can cause everything from gradual degradation to catastrophic failure. So, how do we make sure that the electronics we rely on for mission success are up to the challenge? Here to walk us through this is Jennifer Taggart, manager of our Microelectronics Technology Department. Jennifer, welcome to the show.
Thanks, Kevin. Excited to be here.
All right, well, let's start with the basics first. We talked about the low Earth orbit and Van Allen belts trapping it, geo on top of that, even deep space, and then there's also man-made. Back in the Cold War, we were really concerned about high altitude nuclear detonations as well. Can you talk about what those radiation effects are on our satellites and our systems, and maybe even why does that matter to the mission and how we go about testing those where it's required?
When we're in a radiation environment, we're concerned about parts receiving some of that energy. And then we're also concerned about the radiation penetrating the computers inside these satellites and depositing a very sudden amount of charge, and that can result in bit flips in a digital system. It can also affect the gain of different analog components as well over time. And so the main particles that we're concerned with in the radiation environment are electrons, protons, and then galactic cosmic rays, which are high energy particles that come from outside of our solar system. And so in order to kind of understand all of the effects from those particles that these satellites are living in, we have to go to a variety of different facilities to do those kind of tests. So we can do total ionizing dose testing here at Aerospace using cobalt-60, which provides like a high energy gamma ray that will penetrate through the devices. Total dose testing allows us to understand the lifetime of the computer in the satellite so that we know how much charge it can receive before it starts to degrade and is no longer functional. The reason we would do heavy ion testing or proton testing would be to understand that when there is data that's corrupted, how does that affect the function of the system?
So we understand, though, the degradation of this mechanisms, and I know that we test for that and we can buy radiation tolerant parts. So as long as I've got a part that is spec'd out from the vendor, we're good to go?
Not always. And so certain vendors will perform mil standard testing. So it's a kind of prescripted series of tests that they have to do in order to qualify the device for the space environment. But that is kind of on average the environments that people have traditionally needed. But that doesn't necessarily mean that that is valid for all orbits, for all mission durations. And so if your mission has something outside of the environments tested for following mil standards, then you have to do additional testing. And some parts are not radiation qualified. So there's a lot of commercial off-the-shelf components that they would be advantageous to use in new systems. However, they haven't been qualified for the radiation environment. So if you're a mission designer, you have to include doing testing on those components yourself.
So what goes, there's got to be a lot of trade-offs that go in as a mission designer, especially if I want to fly commercial parts. I want to get the next version of a GPU or a new FPGA up there. How do they factor that into their design process?
So they have to understand that you need to do radiation testing on parts that are not radiation qualified. And so you need to plan for that testing early on in your mission development. And there is also a risk, especially if you wait till the end of your mission planning time to do those tests, that it might not be rad tolerant enough for your interests. And so you would eventually have to switch out that part to something else, and that can push your schedule significantly. So the advice would be that if it's not already radiation qualified, and especially if it's a commercial part, that you need to do that testing early on. And you need also not only do you have to do the testing, but you have to understand how to test it, especially if it's a complex part. You might not be able to follow traditional mill standards to test it just because of the complexity. It's not easy to figure out what the worst case scenario is for operating it.
So this has got to be absolutely critical for the military systems, and to understand what electronic parts are needed to close the mission thread and to be able to test them to get a reliability. Do we have predictive methods to determine how reliable that system will be in the environment? Especially as we go commercial.
Right.
Yeah.
So there's a mix. So we like to rely on physical measured data, because that gives us an idea of what the actual risk will be, because we have that data in hand. Sometimes it's hard to test for every single scenario, and so in that case, simulation is a valuable tool. And simulations also allow us to simulate the projected environment and orbit it'll be in, what the variation in the radiation environment will be over the lifetime of the mission. And simulations can also be used to determine how, for example, if there's an upset in your device, how that signal propagates through your whole system. And so that's part of actually the analysis that they will do as part of their mission, is like worst case circuit analysis, and that kind of simulations are included in that.
Incredible. So, I mean, what I heard is you got to understand your environment, you got to be able to test, and then you can model it in sim to figure out the reliability and the impact on the mission. I want to thank you and all the work you do in the laboratory here to make sure our systems can survive this radiation environment. And I hope you've all understand how important it is to make sure you're thinking through the mission ramifications up front and are able to test and design and select parts that can survive for the duration and in the environment that the mission demands. Thank you again, Jennifer, and thank you all for joining us for another episode of Tech Talks.